Hello and greetings. This is week 5, video 5A actually. This is the week where we cover mathematical induction and recursion. These two topics will not be on the midterm, which is exactly 1 week today. Right now, this is Monday, February 2nd, that I'm making this recording. So that means you have chapters 1, 2, and 4. I'll show you the sections specifically. Let's just do a review first before we cover new material. What we cover this week, like I said, will not be on the midterm. So I give you a week grace, if you will. And so what about this midterm? Okay, it's exactly 1 week today, 50 minutes long. It's worth 25% of your grade, 2 midterms, so 50% altogether. And it will be an AQ 3181. I think you all know that. AQ 3181. I should have put that on this slide, I suppose. I'll post this on Canvas with the address, the class. So that's what we'll be covering. Notice that week 3 we did not cover chapter 3. We didn't cover chapter 3 at all, just sections 2.1, 2.2, and inclusion exclusion, which comes from chapter 8, but you don't really have to go up there. We talked about this already. Okay, so all of chapter 1, not much of English translation, no puzzles. Some maybe logic circuits will be okay, since we did a couple of those examples. Chapter 2, just 2 sections, 2.1 and 2.2. Of course, there's a bit from cardinality. There's a section in 2.5 that's about cardinality of sets, but we'll cover enough of that before actually having to do section 2.5. So omit section 2.5. We've done enough already within section 2.2. Nothing from chapter 3 and 3 sections 4.1, 4.3, and 4.4 from number theory. So in other words, it's the first 4 weeks, not the 5th week, just the first 4 weeks. Class notes, obviously. It's just do problems. That's the only way to really learn this stuff, is to do problems. Keep doing problems. For every hour of class time, you should have 2 hours set aside for homework, just working problems. The more you work out these problems, the better you'll get at it. But you have to actually do them. You can't just look for solutions and go, yeah, I see how it's done. Yes, because you're not learning anything like that. But I've said that enough already, many times. Textbook examples, they're pretty good too. I've been known to just put examples out of the textbook and whatever chapters are being covered on the midterm. I pull no, curveballs on you, whatever. I don't pull any out of the blue type of questions. There's at least one hard question to separate people out, but that's largely if you've been paying attention and you've done the minimum, you'll pass the exam. Okay. Doing the minimum means you do the homework, you work on the material, you don't flake out on it. Then you'll at least pass. But just getting 50 or 60% on the midterm, on both midterms, and then of course, isn't really so good. C minus, D, those are not very good passing grades. You want to do much better than that, and you can just by working harder. I will provide all the axioms. I'll provide, the laws of logic or the laws of set theory. There are no laws of number theory that will be provided. That was just there for your information. Cheat sheets. Well, enough said about that, wouldn't you say? Okay. So that's that. We're back to this screen. I have another thorough review that I've come up with you. Let's just see if I can find it. Okay. Okay. Where is it? Okay, that's not the one I'm looking for. Okay, I thought I'd pulled it out. Okay, here we go. This is it. Oh, come on now. You can do it. Okay, well, this isn't quite the same as the one I I had before. I don't understand what's going on here. Let's see. Where am I getting this from? Sun, Macam. Let's just make sure I know what I'm doing here. Lecture 4.4 point. Number theory. There we go. No. Where is it? All right. Review. All right. There it is. Although it really isn't. There's something wrong here. What the hell have I done wrong? Okay, we'll just have to use this one right here. I don't know what's. I've just did things on that computer over there. Oh, there it is right there. I've got too many copies of this. So let's just run through. I apologize for that. Let's just run through just a brief review and maybe some kind of simple exercises of what we've done so far. So what's a proposition? Obviously, you know what a proposition is. It's a declarative statement that has truth value. What is the difference between logical equivalence and implication? Well, logical equivalence means two statements always have the same truth value, i.e. identical truth tables, okay? Implication means that if one statement is true, then the other must be true, not necessarily vice versa. So you cannot have the case in implication where the hypothesis is true and the conclusion is false. That is how you define the semantics of implication, material implication. What's a contrapositive? That's just the modus tollens of modus ponens. See, if you take here this as implication, it has the same exact truth table, logical equivalence as negate Q implies negate P. You know that, and the converse of P implies Q is Q implies P, and it is the contrapositive as well of negate Q implies negate P. So two sets. Why is the converse of implication not logical equivalent to the original implication? Well, the converse Q implies P changes the direction of the implication. That's a really obvious question. It may be true when the original implication is false, or false when the original is true. Okay, that's basic. Tautology, all your truth tables are true. Okay, the tautology of the compound proposition that is always true regardless of the truth values of its components. So, for example, P and its contradiction, and or I should say, if it's and, it's a contradiction. If it's and or its negation, it is a tautology. It's always true. A direct and indirect proof. Well, the direct proof goes from the hypothesis to the conclusion by deriving a thread of logic connecting the two. So directly from the hypothesis to the conclusion. Indirect proof could be the contrapositive, which is taking the negation of the conclusion and deriving the negation of the hypothesis, or in an identical, that though subtly different manner, a proof by contradiction. Okay, proof by contradiction is the negation of the conclusion, which derives a contradiction, which doesn't necessarily have to be negate Q, okay, or negate P in the contrapositive sense. It could be just negate R, okay, where R is just something else that has to do with the axiomatic system that you're in, say number theory, and it violates it, saying something like 0 equals 1. You might derive that out of a proof by contradiction. Okay, a basic structure. Sets, functions, sequences. Well, we didn't do sequences. We haven't done functions. That's going to be up in the, what do you call it? Up way ahead in chapter 9. So I've shifted it up there. So what's the difference? A subset and a proper subset. You obviously know the difference. A as a subset of B is written like this, which means B can be totally contained. A can be totally contained within B. And here, that's not the case, where A is just a proper subset. It also includes the fact that A cannot equal B. Power set. Well, it's an exponential set of elements with the number of primitive arguments, n. And so the power set of A is just a set of all subsets. Okay, so for example, the nice Wikipedia example of the set 1, 2, 3. And it has 2 to the 3, which is 8 subsets. Every subset includes the empty set, and a subset, every subset includes the set itself. Okay, the set is a subset of A is a subset of B, means A can be contained in B. So A is another element, and then all of the ones in between: A, B, C, AB, AC, BC, ABC. Okay, that's 8 altogether. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I just saw it in my mind. Okay, so that's the cardinality of the power set. Number theory. Okay, we didn't do cryptography. That's like I said, this is oriented towards computing science, of course, but this is a math course as far as I'm concerned. And of course, we've done a little bit of drifting towards computing science, for example, and in terms of logic circuits, we've done some of those things. We do a few things. Cryptography is a little more to it involved, in my opinion. It's something that's very important to modular arithmetic, for example. Like I mentioned before, in quantum computing, it becomes very serious there. And that has to do with cryptography. It has to do with methods of undoing RSA encryption. Some of you know what that is. You don't have to know what that is for this course. So, what is number theory? Well, we begin with the division algorithm. Very simple. A equals dq plus r. Integers a, d greater than 0, there exists a unique integer q quotient such as r. The remainder equals a equals dq plus r. You know what those things. D is the dividend, and q is the quotient. All right. What is the common divisor of GCD? The GCD of two integers is the largest integer that divides both numbers. What does it mean for two integers to be relatively prime? It means that their GCD is 1. Okay, so two numbers are relatively prime if their GCD taken together is 1. And numbers are relatively prime if any pair, as you go along, the sequence of primes is relatively prime, has the GCD of 1. What is modular arithmetic? Well, it studies integers modulo n, where numbers wrap around after reaching n. So it is a special kind of arithmetic that involves. We spent at least 3 slides talking about this in detail. Just look at those slides in 4.1 if you haven't done this already, and just look at the fact that it's different. It's a different kind of algebra because it has to do with cyclic elements. It has to do with cyclic systems. So you're looking for patterns in numbers. It's not just like, you're equating two things together. This is we're talking about modular arithmetic. Congruences, though, on the other hand, are equivalence classes. And equivalence classes are an equal sign is an equivalence class, but a congruence is also an equivalence class, but not like equals. It's different. It has to do with patterns in numbers that cycle, like that clock up there, like that clock up there. I've just moved my like a clock. There's no point in me moving this thing, is there? Unless you actually can see it, but never mind. When are two integers congruent modulo n? Well, here, this is really important, okay? A congruent to B modulo n is the same as saying n divides A minus B. Do not forget that. That is the most important definition of chapter 4, okay? A and B integers are congruent to modulo n if n divides A minus B. We write it as A is congruent to those 3 equal sign horizontal marks to B modulo n. All right, okay. So here we've done little problems like this. We'll just walk through them. I don't want to actually, we've done this already. So here, if an integer A divides integers B and C, then A divides B plus C. I do believe we've done this. It's very simple. If there's 2 integers B and C, then there exists integers K and L if by divisibility. by definition of divisibility. If A divides B, then B equals A times this integer K. And if A divides C, then C equals A times this integer L, okay? And now add B and C together. B and C, if you have your other expressions for B and C, you factor out the common A. There you have it. Since K plus L is an integer, B plus C is a multiple of A, therefore proved. Okay, that's the simplest proof. You all should be able to do that. Every one of you should be able to do a proof like this in number theory. Oh, this gets a little bit more interesting. I'm going to walk you through this slowly. This is a nice one for you to know how things go. So, a proposition for all odd integers n such that n is congruent to 3 modulo 6. 7 divides 3 to the n plus 2 to the n. Now, this might seem like a strange question, but let's just go through it. First of all, express n in terms of an integer. Since n is congruent to 3 modulo n, we can write n equals 6k plus 3 for some integer k greater than 0 or equal to 0. That's the step one. So express n in terms of an integer. It's always the first step when you're trying to prove these kinds of congruences. Always go with the definition. These two are the same, okay? For all odd integers, they're not the same. I'm just saying that this is a congruence and this is a congruence. Now, this is the congruence necessary for this congruence to hold. So we've done the first step. The second step is recall the powers modulo. So let's have a look here. If we cycle up through the first base, 3, then as we cycle through all the different powers, we find that the remainder goes to 1 and it repeats itself after that. So it has a cycle of 6, okay? A cycle of 6, whereas the second base here, 2, if we cycle through, we hit 1, which is the end of the cycle, just at length 3. So step 3 is reduce the exponent modulo the cycle length, okay? So for 3n, 3 to the 6k plus 3, since the cycle length is of 3 modulo 7 is 6. 3 modulo 7 is 6. Yes, that's here. So, yes, also for 2 to the n, we go to 2 to the 6k plus 3, just, these different variables that we've defined up here. And its cycle length is 3, so the length of 2 modulo 7 is 3. So as we did up here instead of 2 to the 6, we got 2 cubed to the, not k, but 2k plus 1, okay, if we just go back to our substitutions up here for the other integers. And it cycles to 1 to the 2k plus 1, which is 1 modulo 7. Here, this one here is 6 modulo 7. So add them modulo 7. 3 to the n plus 2 to the n is, now you just add these modulos. This is modulo 6 mod 7 plus 1 mod 7, congruent to 7 mod 7, okay? That's what these mean when you add them up like this. Okay, so the conclusion is 7 is congruent. To 3 to the n plus 2 to the n for all n integers, okay? Odd integers, for odd integers, okay? So we began with odd integers and we ended up proving it, okay? This you might want to check. So a summary express n as 6k plus 3. That's odd, okay? That's how we did the odd part. Congruent to 3 modulo 6. Reduce 3n mod 7 using the cycle of length 6. Reduce 2 to the n mod 7, reducing the cycle of length 3. So that's these two right here. All right. And so that was what we did. That's that third step. All right, and then sum. 6 plus 1, 7. Um, 7 divides, here you go. 7 divides 6, 7 divides 0 modulo 7, 0 remainder. Okay. So that means it does indeed divide these two terms. There's no remainder, and when you look at this, obviously you can't state this without with a remainder. All right, that's a pretty good problem. Well, Euclid's lemma, it's in summary, if a prime number divides a product of two integers, then it must divide at least one of the factors, at least one. So it's an XOR. It's an and or right here. So if P is prime and P divides AB, then P divides A or P divides B. Why it matters, Euclid's lemma is key reason for prime factorization is unique. We used it for that proof. Divisibility arguments using primes work. Okay, and many results about GCDs and congruences. Okay, so typical use breaking divisibility of a product into divisibility of factors. That's very important. You can appreciate the value of that statement. Proving results about coprimes, obviously, which is related to the first one. Establishing properties of prime factorizations. All of these are obviously related. And so here we did this one already in class. We did this. If P is prime and P divides all of these integers, then it divides each of them individually. All right. So primes cannot hide inside a product. If they divide the product, they divide a factor. Right. That's what that says. And it's nice to put it here. This is, of course, some AI's way of stating this, which is kind of cute. Oh, by the way, I sure hope you notice that ChatGPT is extremely problematic. It is unbelievable how bad. You can read it on Reddit too. People are all talking about it. There's better places to go than ChatGPT. I can assure you. You can find them on your own if you like. ChatGPT, I can tell you stories about my experiences with it. It's an excellent editing tool, but it makes a tremendous amount of mistakes in derivations and mathematics. You have to watch it with a keen eye, which is really good because it forces you not to just take it for granted. Whatever results you get from ChatGPT, plugging stuff from this course into ChatGPT, you've got to look at it and understand it to make sure that it gave you the right answer. At least it'll give you hints if you're lost, but it's better to do that in the tutorials. Primes and greatest common divisors. In plain language, these problems study how numbers factor into primes and how much two or more integers have in common, using the greatest common divisor to measure the overlap. Okay, so prime factorization, every integer is greater than one. Every integer greater than one factors uniquely into primes. That's prime factorization. Greatest common divisor. The GCD of AB is the largest integer dividing both A and B. All right. Coprime, we've talked about this up here already. GCD of AB equals 1 means, I love word. Means that the numbers share no prime factors. They share no prime factors, okay? Key theorems, Euclid's and Bézout's identity. Okay, Bézout's identity was useful for calculating, for our case, calculating inverses. So no Bézout's identity. Those are key theorems of chapter 4. Euclid, Bézout's identity, and of course the Chinese algorithm. So, okay, we know what primes are. We know what divisibility is. We're sort of going in circles here. Solving linear congruences. Okay, this is very important. This is section 4.124, something like 134. Yeah, section 4. So here, this variable x is what we're trying to solve for, and we can have this is called a linear congruence. And we can have systems of linear congruences, just like in linear algebra, we have systems of linear equations, right? So solve a linear congruence of the form ax plus ax is congruent to b mod m by determining whether solutions exist, and if so, finding all solutions modulo m. That's kind of obvious. Why such problems typically involve what they involve. Checking existence of solutions. A solution exists if and only if the GCD of AM divides B. Okay. Reducing the congruence. Divide by GCD AM if possible. Sometimes it's already done for you. Finding the modular inverse. We spent a lot of time on that. I've given you a paper on the Chinese remainder theorem. Study that thoroughly. I've already warned you or given you a heads up that something on that or something like those problems and that I think it's 4.2. Let's have a look at which one it is. 4.6, that one right there. Study it well, okay? Finding modulo inverses when GCD AM is equals 1, you compute the inverse mod m, okay? That was the algorithm. You have to go back and review it. It's a little bit involved. Okay, remember, we can't divide, which is what you typically do with arithmetic to find an inverse. Like the inverse of 6 is 1 over 6, you know? We can't divide here. We have to use a multiplicative inverse, and that's a to the minus 1. Just like in function theory, f to the minus 1 of f of x is x. F to the minus 1 undoes f, okay? What's this? Writing the full solution set. Solutions are given modulo m, or m is divided by GCD AM. Okay, so that's solutions for a given modulo m. Okay, I have to think about what this says right here for a second. Here, just hold. It doesn't matter. We didn't really do much about this. Hold on the fourth. I've got to check what's said here. There's an ambiguity with the slash. It's often said to say or, but that's been said already, or has already been said here, so I'm not sure. This is m divided by GCD of AM. I'm going to have to make sure that is what that is. Typical problem statements. Okay, solve 5x congruent to 3 mod 14. Find all integers x such that 12x is congruent to 8 modulo 20. Determine whether a solution exists for this linear congruence. So problems about solving linear congruence involve finding all integer solutions to modular equations of this form. We've already said that. Okay, this is just an example. Here's where you're looking to see if numbers are coprime. We've gone through this already. Okay, this is a good example. Factorization of primes. This is just again summarizing what we've done in chapter 4. So we identify the GCT with factor 210 into primes and identify the greatest common denominator with 84. And so 210 factors out like this, 84 factors out like this. Common factors are 2, 3, and 7, obviously. 5 isn't. So the GCT of 210, 84 is 42. Okay, that's right there, the common factors. Now here's the big one. Okay, you gotta really know this. All right, so it answers this kind of question. I know the remainders of a number when divided by several numbers. Can I figure out what the number is? Remember, there's this famous Chinese puzzle that was set out centuries ago that the Chinese remainder theorem addresses. So example, a number leaves remainder 2 when divided by 3. It leaves remainder 3 when divided by 5. Can we find a number that satisfies both of these? And yes, if the divisors 3 and 5 in this case are co-prime, sharing a common factor, there is exactly one solution modulo the product. Here it's 3 times 5 is 15. Okay, there it is right there. So that satisfies these two statements right here. A number leaves 2 when divided by 3. It leaves the remainder 3 when divided by 5. So that is, for such a simple system, how to implement the Chinese remainder theorem. So key points: divisors must be co-prime. Solution is unique modulo the product. Why it works: intuitively imagine a clock for each modulus. Mod 3, okay, mod 3 clock, number shows 2. Mod 5 clock, number shows 3. Okay, so that's how it cycles. That's the pattern that you're looking for. You're looking for a number that lines up on both clocks simultaneously. Okay, so you got two clocks running here with these two statements, and when they're simultaneous, that's when it satisfies both. Does that not make sense? Okay, so mod 3 is okay, we've already gone over this. You're looking for a number that lines up both clocks simultaneously because the clocks are co-prime. There are single alignment patterns that repeat every product of the clocks. Okay. So the recipe is write the congruence. There it is. And there's a system of these things. Make sure M1 and M2 are co-prime. M1 and M2, these remainders. Solve the congruences one by one using the Chinese remainder theorem. To construct the solution, the final answer is unique modulo M, big M. Remember when we went through this? Big M is equal to all the sum of the little m's all the way up to k, sub k. So here's a simple example with numbers. X is congruent to 2 modulo 3. X is congruent to 3 modulo 5. How do we find X? How do we solve that system? List the numbers congruent to 2 modulo 3. There are 2, 5, 8, and 11, and so on. It just keeps going. Which of these is congruent to 3 mod 5? Well, only 8 is. Only 8 is. Okay, so the solution is 15. 3 times 5 is 15. Yep. 3 times 5 is 15. Okay, so X is congruent to 8 modulo 15. So that is how we solve that congruence. Remember, what we're doing here is solving for X in a system of linear congruences. Okay, so the China remainder theorem lets you reconstruct a number from the remainders modulo several co-prime divisors. That's what this is up here. These two, just two of them, giving a unique solution modulo the product of those here divisors. So that's X is congruent to 8 modulo 15. Here's another one. So we have a system of 3 linear congruences. So solve first. The first two, X is congruent to 2 modulo 3, implies X is 3K over 2, obviously, from the definition. Plugging into the second, we end up with K is congruent to 2 modulo 5 from that substitution. So K equals 5 plus 2, which implies X equals 3 times 5M plus 2 plus 2. That's 15M. If you work out the math, plus 8. So then you solve modulo 7. 15M plus 8 is congruent to 2 modulo 7 means 15M is congruent to minus 6 modulo 7, which is congruent to 1 modulo 7. So 15 is congruent to 1 modulo 7, implies M it's congruent to 1 modulo 7. That's what we're looking for. And therefore, M equals 7t plus 1 implies X equals 15, and you're substituting now as 7t plus 1 plus 8. And here you work that out. It's 23, which equals 105t plus 23. So that means the general solution for X for this system is 23 mod 105. And I'm just trying to figure out where did we get the 105 came from I have to look at that. I have to make sure that's correct. That doesn't look correct. Okay. I'll check it out. I'll check it out after. There's two things I want to check out. Okay. This one, you can go over this yourself, checking divisibility, which are um, seemingly difficult looking. They're intimidating when you have these large powers, but they're not. They're not. We did that already. And a similar problem above, which had the sum of two exponentials, base 3 and base 2, just like this one. You just follow through the same way that went through. And here, just a very simple solution of a linear congruence. So this Chinese remainder theorem, again, it's just we've done it already. We've done it. Okay, I'm not doing cryptography. So, okay, that's it for now. That's it for a review, I think. I think you've got pretty much all you need right now. I'll post the, let me just give you an idea of what's coming. All right. Here, I'm going to have to just set this aside and try and solve it, find out what's wrong with it. Here, let's just see what's coming. I mean, I hope you all can see this. So what we're going to do here is we're going to talk about these repeat. This is a proof technique for positive integers, all natural numbers. Okay, so positive integers or positive integers including 0. Those are natural numbers. And so once you show that the base can be toppled, then at any part in between, if you a kth domino can be toppled and topple the next one, if you can prove that it can topple the next, then that's just repeated modus applications of modus ponens. P implies P plus 1, and so forth, okay? So it's called the principle of mathematical induction, and like I said, it's for solving problems of that nature, usually series, infinite series, and so forth. And it's also related to recursive sets, so that's part of chapter 5 as well. I mean, here's a nice geometric proof, for example, that the sum of the first n integers is this closed form expression. Okay, this is an open form expression. This is a closed form expression. Here's an interesting geometric proof. We don't like geometric proofs because they're just not formal enough. So we do different things, okay? Okay. I say. Okay, some of these slides have to be taken out. Okay, I have to revise this. It's a good thing I looked at it. Yeah, that's definitely it. I've got to solve a lot of problems here. I will take care of that right now and be prepared for one more at least, or two presentations probably on Monday, Tuesday, tomorrow. Okay, even though I have to go all the way to Chilliwack to my doctor in the morning. Who cares about that? I'll get it done. So please, go to your tutorials. You must do that. Work out all these odd problems. You have answers in the back. If you do just that, and you do it, with confidence, you will do well. Don't forget that I've chosen a few problems that we've looked at, some particular proofs, for example, and said, this might be on the midterm. Of course, I said that this Chinese remainder theorem PDF that I sent you, definitely know that like the back of your hand. Okay? Well, thanks for now, and cheerio.